So again, we have to start by telling Python and telling the notebook what knowledge it needs to do the calculations. So this time, we're also going to import the same ones as before. We're also going to import this module called pandas, which is good for handling data sets, and some code for making nice plots called matplotlib. So we can run that, and it takes a little while. Okay, so once that's run, we can read in a data set. And so this file is located in the same directory as the notebooks. So if I was to go back to this open screen, the Excel file is just here. And you could download that if you wanted somehow, I think by checking the box on this screen. But so we're going to tell VESIcal to read in this file, and we can point it to a particular worksheet, and we can tell it that all of the data is in weight percent. And that runs. Ignore this warning. And then, well, we can check that it imported correctly, and we've actually got some information there by using, so we've labeled it my file up here, and we can say get data from this file. Again,
this is always worth doing and checking your oxides, because sometimes if you've copied from a supplement from someone's paper and there's like a weird subscript for the 2 or like a space, you'll see that an entire oxide column will be empty. So I would always like look and check you've got oxides for the ones you expect, like aluminum, and here you don't have an oxide for chromium, and that's fine as long as you didn't enter a chromium content. If you did enter a chromium content, go back and look at that, if that makes sense. Just to answer your question, there's 2 kind of types of errors and warnings in Python. What happened up here, this pink one, this is a warning, and specifically it's a depreciation warning. So that's warning the people who've written the code that at some point you're going to have to do something, otherwise it's going to stop working in future. As a user, you can ignore them. They're for us to worry about. When you get an actual red warning, like where it prints actual red text and gives you lines, that's a true error that you need to worry about. But just ignore these pink boxes for now.
And I think this actually comes from the underlying thermo engine code. So hopefully that will be fixed. So much the same way as before, we used a very similar syntax. So this calculate saturation pressure. So I should have said we're going to calculate the saturation pressure for each inclusion in this file. So we've got the water and the CO2 contents loaded in. And we have to tell it which column the temperature is stored in when we run this. And instead of running it by writing v dot, which we did before when we were running a single sample, we now run it from this my file object. But again, if that doesn't make sense, it doesn't matter. You just need to know how to replace the file name, and you can use the code that we've already written. And we're storing it in this, the answers in this variable here. So we run that. And it takes a little while because there's a lot of inclusions for it to work through. And because we didn't specify a model, it did this using the MagnaSat model. So we can view the results. So it's printed another table out, and we have to scroll right this time, and we get to this column. So saturation pressure in bars in VESIcal, and we have a set of saturation pressures here. And it also gives us the fluid composition that will be in equilibrium with it. And it's great that we can see it in the notebook, and we could do tons of things in Python with that variable loaded there. But at some point we need to move it out of Python. Maybe that's to submit to a journal. Maybe that's to go and plot in another program or do calculations in Excel. And so we can save it as an Excel file with a name that we specify. And again, we get a warning about deprecation, which we can ignore. So I mentioned that we were bringing in some knowledge about plotting data. So that's what we're going to do here. And I'll just run the cell so you can see what it does. It gives us a nice output. And the instructions that I had to give Python to do that started off by saying, I'm going to make a figure and it's going to have a set of axes on, which is this command here. And then we want to actually tell it what to plot, and we wanted to make a scatter plot. So very conveniently, it's intuitively named scatter. And we say, well, we want you to plot silicon versus saturation pressure here. And then we can add labels to the axes and then show the figure. But we could also save the figure using this command in the cell below. And we could replace the PDF with a PNG file or an SVG file, and it will save it appropriately. So what the plot's showing here is we use MagmaSat, and MagmaSat takes in the composition of the melt inclusion. And so we see variation partly controlled by the silicon content, but mostly by the CO2 and water.
Simon, can you just quickly explain a little bit in more detail how pandas works, how you're extracting those columns?
Yes.
In a separate cell, just to show you how that works.
Yes. So here, this was the variable that we stored the results in, satp magmasat. So I'm going to drag this out, just copy that. And so if I were to just run that on its own, it gives me this information. So that's the information that we're passing to the plotting function. And so this is using this module called pandas, and there's various ways of extracting and pulling out data and filtering data from pandas. And there's tons of information online.
So you might also see it written like this, and that does the same thing. So generally, you just, whatever your column heading is, you can either do the name of the variable dot the name of your column heading, or the square brackets with the quotes and the name of the column heading. So
square brackets is a safer bet, because if you try and pull out a column name, there's also some operation, something that pandas knows how to do. For example, if you have a column that's called T for temperature, what's pandas actually reads that as oh, they want me to transpose the data table, so turn everything round by 90 degrees, which causes lots of confusion. So it's always safer to do this. So I think I've got some suggestions for things you can do to play around with it. We're running out of time, so I'm going to move on to this next bit, but play around with that in your own time and keep asking us questions if you want. And so we use MagmaSat, and we can now do the same thing for using the Dixon model. So here we've got exactly the same command again, but now we've got this added line that says model equals Dixon, to specify it. And we're storing it in a new variable. And then I've pretty much copied and pasted the same code for making a figure. I've just changed the variable name here so that we can plot saturation pressure we get from MagmaSat. This is a saturation pressure we get from the Dixon model. And there's quite a big difference again. And I think, is this a good point?
I think do the isobars quickly.
Okay.
And then we can, because I do that all in the theory, then we don't have to swap around screens too much.
Sure. So Penny will come back to where this is coming from. And there's some hints here where you see to get you to work through how we made that observation, got that understanding to begin with, if you want to do that later. But a very common thing you see in papers that has been quite frustrating to calculate yourself is these plots where there are isobars. So you've got water versus CO2, and then a line that shows, this is all the contents that can exist at a particular pressure. Well, this is very easy to do in VESIcal, and you can make hundreds of these very easily. Well, these only apply to one single composition. And so we need to pull out a composition to use. And here's some code that's going to pull out this particular sample from the data set we've already loaded. And again, I'm skipping over this code really fast because you can go back and look at it on your own, but actually the important thing is just knowing that you can do it, that the functionality exists. So that's read that into this sample variable. Oh, and I said I'd mention how you can get documentation, and I've put this here. If you ever get stuck and want to know what a function does or how to interact with a function, you can write it out here. So this is the file, and this get sample composition function, and put a question mark after it, and it gives you a load of information about how to use it and things it's expecting and what you can do. But back to the calculation. So we're going to calculate all of this using that sample at 1200 degrees C for these 3 pressures. And I'm also going to make some isopleths at the same time. So lines of constant fluid concentration. So store those as variables and then pass them into this method here. And actually, I'm just going to demonstrate something very quickly. These methods exist in the notebooks we've made for you and in the documentation. But if you can't remember what it's called, I have to do this all the time because I don't remember code I've written myself. You can write V, so that's accessing VESIcal knowledge, dot, and then press tab. And it will give you a list of all the different things you could do. So these are all the different calculations you could do, for example. But let's run this calculation. So we'll calculate our isobars and isopleths. So this is a good question, and I meant to say this earlier. Thank you. There is a star that appears when a cell is running. And while that star is there, you know it's doing or trying to do something. If it gets stuck for hours on end, then you've got a problem. and if ever that happens that it's just crashed, you can't do anything, you can restart it's called restart the kernel, which is kind of restart Python, and then you have to.
Do you want to just show them how to do that, Simon, even if you don't actually click it?
So there's this circle here with an arrow. You can redo that, or you can go up to kernel and go to restart.
So something you'll notice that Kayla and Simon have done a great job of writing in is for these slow calculations, it is printing your progress. So you can see it was saying like calculating isobar 1,000 bars, instead of just wondering like, is it doing anything? It's slowly printing like doing 0.25 isopleths, so that if you see those messages changing, it is slowly chewing through stuff. So that can be useful as well.
Yeah. Now, this information's been stored in this calculate object, this calculate thing called calc. So we have to go and get the result in the same way we've done before by doing this calc.result. But this time we've got 2 things stored in the results, so we can extract it by saying there's a thing called we're going to call isobars and a thing we're going to call isopleths. Again, you don't need to worry about what's going on, just that's how it works. And then we can look at what that information looks like. So this is what the Isobars table looks like. So you see this is truncating it because there's so many lines. And we start off with 1 kilobar and the H2O and CO2 dissolved at that point. But maybe we only want to see the results for 1 kilobar. Well, you can use the pandas notation to do this. So we're saying, we want information from isobars where the isobar pressure is equal to 1,000 or a kilobar. And we get a new table back with all the results. But in reality, you don't want to see a table most of the time. You want to see a nice plot. And so we'll see that this code that I just wrote is repeated down here. And I'm not going to go through now. I don't have time to go through now exactly what this code is doing, but I've written some description there if you want to see it. But again, you could go and change the composition if you want and just recreate exactly the same plots for another rock without really having to know what the code does. We get a plot down here. So we've got the 3 different isobars, and then I've plotted the melt inclusion data on top.